We've looked at some types of window functions, and now we're going to cover the rest. Welcome to this video on window functions. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video of this series, I showed you 5 categories of window function, and then we looked at 2 of those categories in the demo. In this video, we're going to finish the job. As a quick reminder of our 5 categories of window function, let me quickly go to the classroom and we'll talk about them. The first category we covered was aggregate window functions, such as min, max, and sum. We saw that all of the aggregate functions can pull double duty as window functions. The second category is ranking window functions, like row number, rank, and dense rank. In this video, we are going to pick back up from there with offset window functions, such as lag and lead. Then we'll cover statistical window functions, such as %rank. And finally, we'll look at ordered set functions, which again are not actually window functions, but they are interesting and related enough that it makes sense to talk about here. Now let's get into the demo and dive into these 3 remaining categories. Here we are in Visual Studio Code. In this video, we'll pick up where we left off in the prior video. We'll start with offset window functions. There are 4 of these that SQL Server makes available. The first 2, and by far the most important, are lag and lead. Lag looks at the prior record in a frame, whereas lead looks at the next record in a frame. Just like ranking window functions, offset window functions require an order by clause. To demonstrate these 2 window functions, I'm going to start with a common table expression that aggregates line profit by invoice date, and we'll call that daily profit. Running the contents of this common table expression, I have 2,709 rows to play with. The main query has a variety of lag and lead calls. The simplest form of an offset window function is a 1-parameter lag or lead call, like what we have on line 233. We lag daily profit. In other words, I want to know the prior record's daily profit. How do I get the prior record? Well, that's something we define in the over clause. Our window definition has us order by invoice date. Thus, what we will get is the prior record's daily profit. But there is an optional second parameter as well on here. How many records do we want to move backward or forward? I can, of course, set this parameter's value to 1. So line 234 will behave exactly the same as line 233. But I can also use other natural numbers and get other numbers of records back, like 2, 7, or 14 in this example. Lead works exactly the same way as lag, except that we are moving forward in our frame instead of backward. Let's run this query and see what we get. Now, throughout this description of lag and lead, I've been very careful not to say something like number of days back, because lag and lead make no guarantee on time intervals. Yes, we aggregated the data by day, but if we look at rows 11 and 12 in this data set, we can see that there were no sales on January 13th of 2013. Thus, lag for January 14th looked back at the row on January 12th and returned its data. We'll talk a little bit more about this later on in the series, but for now, I will simply note that lag and lead are row-based, not interval-based. Still, if we look at the rest of the rows, we can see that the 2 functions perform exactly as we would expect. If we try to get a lagged record prior to the first record in the frame, we get back null. The same will apply if we try to get lead after the end of the frame. Otherwise, we move back the requisite number of rows and return the daily profit for that row. This is fantastic for things like prior period comparisons or understanding the behavior of nearest neighbors. Lag and lead are 2 of the most frequently used window functions, in my toolbox at least. Now, let's move on to the 2 I almost never use, first value and last value. These return the first and last values of a frame, respectively, and like the other offset window functions, they require an order by clause within the window definition. Starting with the same common table expression as before, let's run these two functions. We can see that the result of first value is the same for each record, $14,346.50. But the result for last value changes on each record. Before you go screaming, "It's a bug!" I want to point out that we are using the default window frame. And for offset window functions, the default window frame is range between unbounded preceding and current row. In other words, our window stops at the current row, so last value will give us the current row. If we don't want that behavior, we'll need to specify the frame. Instead of unbounded preceding to current row, let's switch it to range between unbounded preceding and unbounded following. Now, when I run this, we get back what we want. $14,346.50 as the default first value, and $441,896.70 as the real last value. And if you're curious, I don't need it to start with unbounded preceding. I could instead have it start with current row. Note that the left-hand side of the frame cannot use the following keyword, so I couldn't be clever and say range between unbounded following and unbounded following. That would just return a syntax error. But starting with the current row, it's absolutely fine, and the results are the same as we see here. I also wouldn't anticipate that this would actually provide a performance benefit. Admittedly, this is not something that I have tested thoroughly, so there might be a possibility, but my expectation would be it's probably not going to be a big factor for performance. Now, offset window functions also behave the way you'd expect when you put partition by clauses in them. Here we have per customer daily profit. Let's get the amount of profit from the first day a customer made a purchase from us, as well as the profit from the last date in which a customer made a purchase with us. The only difference in these window functions is the partition by clause. Looking at this, we see customer ID 1 has a first value of $316 and a last value of $249. The daily profit for row 1 is indeed $316. If I scroll down, it's going to take me a moment, but I will eventually get to line 714, which is the last day with sales for customer ID 1, and its daily profit was $249, exactly as we expected. Then for customer ID 2, the value is reset. By the way, so far I've primarily used the default sort direction in my Windows order by clauses, which is to sort ascending, but I can sort descending, just as I could with a result set. Here I have two variants of my first and last values. First and last values sorting on date ascending, and first and last values sorting on date descending. My expectation with this is that the two columns that generate first values and last values respectively, their values will be reversed because one is looking at rows from earliest to latest, the other is looking at rows from latest to earliest. Running this query, we can see that the behavior is exactly as I described. Let's take a moment and talk about statistical functions in SQL Server. There are a few of them, and the easiest to understand is %rank. My starting data set is once again a summation of line profit by customer by date. The window function will operate over that data set. To understand how %rank works, imagine that you have a data set. Lay out each row from end to end, sort of like numbers on a number line. Starting from the beginning, how far along this line or line segment do you need to go in order to reach a particular row? What percentage of the line segment do you need to traverse? That is %rank. In this case, I'm going to order by daily profit so that the record with the smallest daily profit will be at the beginning of the number line, and the record with the largest daily profit will be at the end. And then each row will be equidistant from each other. So again, like a number line, you go 0, 1, 2, 3, etc. In this case, you'll have first row, second row, third row, etc. We're not thinking about the distance between values in terms of cardinality. We're just thinking in terms of ordering of these rows. Running this query, which sorts by %rank descending at the end, we see one record with a rank of 1, or 100%. That record has the single largest daily profit. The second largest daily profit has a % rank of 99.9998%. That's a very large number, and it happens to be 509,218 divided into 509,219. As I scroll down through here, the percent rank value decreases as we would expect. And if I run into any ties, all of the tied results share the same percent rank. So that behavior is akin to the rank window function. Makes sense given the name, after all. And scrolling all the way to the bottom, we see that the lowest row has a percent rank of 0. Now let's take a peek at percent rank by customer. I'm partitioning by customer ID and still ordering by daily profit. And this time, I will also order the final result set by customer ID and then percent rank ascending. For customer ID 1, we have one order with a value of negative $96 at the bottom rung. If I scroll down to line 714, again, forgive my slow scrolling, but we will eventually get there. And I'll get to the largest value for that customer, which is $14,085.50. If I want to know what the 50th percentile was, I can scroll up to where percent rank is right around 0.5, and it looks like the median value would be $651.70. The reason that I know this is because we have an even number of records. So I need to take the value closest to the 50th percentile but below, and then the value closest to the 50th percentile but above. And in this case, those are $651.50 and $651.90, respectively. Add those two together, divide by 2, and we get our median. That's quite a bit of effort to calculate a median, but there is a better alternative coming up. The next window function I want to cover is the cumulative distribution function. This behaves similarly to percent rank, but the definition is slightly different. As I mentioned before, percent rank is essentially what percentage of the number line do we need to traverse before we reach this record. Cumulative distribution, meanwhile, asks what percentage of records have a value equal to or less than this value. For this reason, the first row's cumulative distribution is 0.0014, not 0 like its percent rank result. That's because 1 out of 714 rows have a value less than or equal to negative $96. Now, in looking at the first several records, you might be saying to yourself, hey, it looks like cumulative distribution is just the lead of percent rank. That's not quite true for two reasons. The first reason, as we can see on line 10, is that it doesn't quite hold up. Notice how there are 3 records with a value of $16. Both percent rank and cumulative distribution have the same numeric value for those 3 records. But then the value of cumulative distribution is 0.016867. And by contrast, the percent rank on line 13 is 0.1683. That's very close, but it is slightly different. This boils down to the behavior with ties, and you can see from there that the two numbers stop matching perfectly. Second, as we get closer to row 714 and the end of customer 1, these two values will converge until both of them have 100% on line 714. As far as which one to use goes, percent rank is nice if you're working in percentiles, whereas cumulative distribution is necessary if you're trying to understand the empirical distribution of a dataset. If that last sentence made absolutely no sense to you, then you probably don't need to use either of these functions. But quite often, we care about the inverse of the above problem. Percent rank helps us answer the question of what percentile a given row is in the dataset. But often, what we care about is the value for some given percentile or set of percentiles. And that is where percentile cont and percentile disk come into play. The former is a continuous calculation, and the latter is a discrete calculation. And I'll talk about that in just a moment. First, though, I want to point out that percentile cont and percentile disk are special types of window functions, as they have not only the over clause that defines a window function, but also a within group clause that we will see with something called an ordered set function later. Inside the percentile function, we have a decimal value that represents the percentile we'd like to collect. In this case, I'm going to show you the classic 5-number summary for a dataset. That is the minimum value, the 25th percentile, the 50th percentile, the 75th percentile, and the maximum value. This gives us a good feeling for the midpoint of the data, the entire middle half of the data and how wide it spans, as well as how far out the ends stretch on either side. We'll partition this by customer ID, returning the percentiles ordered by daily profit. It's important for us to put the order by clause within the within group segment of this query, as we are grouping by customer ID and then ordering. Running this query takes a little bit of time to complete and returns 509,219 rows, one for each customer ID and invoice date combination. Now, I've sorted this by customer ID descending to make things a little easier and a little bit more interesting to read, as we keep focusing on customer ID 1 and its 714 rows. Instead, let's take a look at customer ID 1133. It has a smallest value of $690.30 and a largest value of $1,060.50. The interquartile range, that is the middle 50% of the data, says that it spans $707.33 up to $1,023. We can perform the same calculation for each subsequent customer. But one important thing to note is that there are no records for customer ID 1133 with a dollar amount of $861.75, nor $707.33 or $1,023. Because we only have 4 records, the median is the midpoint between the second and third largest records, and the 25th and 75th percentiles similarly will also be midpoints between records. The continuous formulation of a percentile calculation is mathematically correct, but if I want to return the values associated with the median record, I will have some trouble finding it because I can't search where daily profit is equal to $861.75. I won't get a row back that matches that exact number. This is where discrete percentiles come into play. In this next query, I'll change 2 things. First, I'm going to sort by daily profit to make that explanation a little bit easier to read. Second, I'll include only the median, again to make my explanation a little easier to follow. I will include both the discrete and the continuous percentile calculations of the median, and the operators will otherwise be exactly the same. Running this query, I can see that the discrete value of median is $713, and our continuous calculation of median is still $861.75 for customer ID 1133. As I mentioned, if we have an even number of records and we want to calculate the median, we take the middle 2 values, sum them up, and divide by 2. Here, customer ID 1133 has 4 dates with sales, so we take the second and third values. Those are $713 and $1,010.50 respectively. Sum them up and you get $1,723.50. Divide that by 2, you get $861.75. By contrast, the discrete median takes the smaller of the 2 values and thus returns $713. Let's scroll down just a little bit to customer ID 1131. This customer has an odd number of sales. Specifically, they had 11 sales. When the number of records in a set is odd, our calculation of median is simple. We take the single record in the middle of this ordering. That would be the 6th record of 11, which happens to have a value of $280. And because we have that single record, the continuous and discrete calculations will return the same number. Which one of these you want to choose will depend on your purposes. If you want to guarantee that you can search for records whose values are equal to the median calculation, you'll want to use percentile disk. But if you want to calculate a proper median, percentile cont is necessary. As the number of records increases, these two tend to be fairly close together, though the discrete median will always be less than or equal to the continuous median, and I'm sure you could rig up a data set with hundreds of thousands of rows where the two are wildly different. But that's neither here nor there. I will give you one warning with respect to these percentile calculations. They can be extremely slow, to the point where, with a large enough data set, the query may never finish in reasonable human time. If I enable the actual execution plan and then I run this query again, it will take a little bit of time to run, but it will also give us an idea of why this can be so slow. This is an execution plan for a single discrete percentile and a single continuous percentile per customer. We start with an adaptive join of invoices to invoice lines. Then we hash match the data to get 509,219 customer ID and date combinations. We sort this data and feed it to one window aggregate. Then, after a compute scalar operation, we sort and perform another window aggregate. Then we sort, have a pair of scalars, and go through yet another window aggregate operator. Then we have 3 compute scalars, another sort, another window aggregate, and finally a compute scalar and a sort to round things out. By my count, that is 5 sorts and 4 window aggregates to resolve this query. If you have a billion rows in a data set, that's a lot of sorting and a lot of aggregation that you're going to have to do. Now let's talk about the final class of function, ordered set functions. These aren't actually window functions, but they are second cousins, so they're close enough. SQL Server 2022 has a few of these. The first one to arrive was string ag, which we saw in SQL Server 2019. Suppose I want to build a comma-separated list of elements. In this case, I have a list of territories associated with the United States, the 50 states and commonwealths, as well as Puerto Rico, the Virgin Islands, and District of Columbia. Each of these territories has a region associated with it. Let's suppose I want to get a comma-separated set of territories for each region. Prior to SQL Server 2019, the most common way in which we would do this involves taking advantage of 4XML path processing that has been in SQL Server since 2005 and using the stuff function to put together the list. I would not claim that this T-SQL is particularly intuitive, and hopefully you wouldn't either. But as we can see, it does work. As of SQL Server 2019, we have the string ag ordered set function. This is an aggregative function, so we need a group by clause containing the sales territory name because it is not part of the function. But in just a few lines of code, and with a fairly straightforward function call, we have the same results. Now suppose that I want to sort the states within a territory in alphabetical order. I can do so easily using the ordered set syntax, which is the within group operator. Inside of each sales territory grouping, I want to order my results by state province code before aggregating the string and concatenating each element with a comma. If we run this new query, we can see the states show up in alphabetical order within a sales territory. SQL Server 2022 gave us a pair of new ordered set functions. I talked about percentile cont and percentile disk just a few moments ago and mentioned that these can be very slow to the point of not completing in a reasonable amount of time with a large enough data set. This is why Microsoft introduced approximate percentiles in SQL Server 2022. Here's an example of how to use approximate percentiles in a query. Note that these are not window functions, as there is no over clause. We only have the within group, indicating that these are ordered set functions. Approximate percentiles run approximately 2 orders of magnitude faster than precise calculations, and there are some guarantees around how close the middle ranges of data are. Let's calculate approximate 5-number summaries for each customer. It takes less than a second, and we have our results. The min and max data points can be quite off from actual values, but the interquartile range will be pretty close on the whole, and I'd like to demonstrate that with the final pair of queries. Now, to make things easier, I am going to calculate a single 5-number summary across all 500,000 rows. The first query is approximate percentiles, the second query is actuals. In both cases, I'm using the continuous function instead of the discrete. And when I run these, we can compare the values. As you can see, the min and max are way off for my approximations compared to the real values. But the median, as well as the first and third quartiles, are within approximately 1% of the actual value. And most of the time, you will see this. There's some calculations around the boundaries of how far the formula can be. And in general, what I've noticed is you're about 1% off if you stay within that interquartile range. In most cases, when we're looking for a median, it's not so much that we care precisely what the value of the median is, but rather that we get something very close to the actual median. If I say that the median is $707 or $703 when it's really $705, well, that will rarely change any sort of business planning or calculations. And if that difference is enough to change a decision, well, that's when we go get the actual median. And that's going to do it for the classes of window functions. Over the course of this video, we looked at offset window functions, statistical window functions, and even some ordered set functions. In the next video, we'll look at some clever use cases for the 5 classes of window functions and see how you can solve common business problems with them. We'll have links and show notes in the description below. Until we see each other in the next video, take care.